And actually, that's not so bad, is it? We have a policy. So we have, in policy iteration, you get a policy and then you update it by solving a Poisson equation. Now, Pn is the transition law you get with the nth model, and Cn is the cost function of the nth model. What is Pn? Well, Pn corresponds to the system with state feedback. Again, so the cost is the cost you get with that control. Okay, so I plug in u equals minus k and x in this control. What am I going to get? I'm going to get 1/2 x transpose kn transpose q kn. So this was knx was equal to knx, and that should not be a q. I heard somebody say that. That was a test. That's one of the questions I'm making. The q is not equal to r. All right. So what happens is that what you get is, get out your different colored pen. We just have an uncontrolled model. There's an an there. And this is just 1/2 x transpose q n x. So for Poisson's equation, we have an uncontrolled model with some matrix an, and we have a new quadratic cost. And we saw that the solution to Poisson's equation was the Lyapunov equation. So Hn is equal to that, where Mn solves the Lyapunov equation. What was it again? Mn so there you have it. Okay. And we know what eta n is as well. We know that it was my So go back to your notes. So when I first looked at the linear systems, I said, let's look at the uncontrolled case. I said, if we want to solve Poisson's equation like this, with sweep quadratic for a linear system, that's equivalent to a Lyapunov equation. And so we're just looking at the closed loop A matrix and the, if you like, the closed loop cost. And so you solve this equation, and you get eta n, and that's it. And what do we know? We saw if V0 is a Lyapunov function for some policy, then we know that these 8 ends are decreasing. So that's what we saw, our theory. And I'll go, that's not a very precise statement of the theorem. You can go look at your notes for the theorem. But you have a Lyapunov function, it's not very specific, and then Poisson's inequality. Anyway, so this is true. So the 8 ends are decreasing. And, yep.
So we initialize the kn with the k0 that is for that Lyapunov.
Yeah, that's right. Yeah, that's right. So yeah. Well, that's right. I haven't done the policy update, but it's a policy update as well. Yeah. So. You choose K0 is the policy you get from V0 is a minimizer. I love that stuff. So this is true. So the data is decreasing. In fact, in case of a stronger theorem, I can kill this. So I'll put it down here. 3 policy update. I'm not going to put that down. So we saw how to update the policy given a quadratic function. So it's true theorem. Under the conditions of under the stabilizability, detectability. So the detectability is a relaxation of the conditions I had before. In our theory, I needed something stronger. I needed this coerciveness condition. So the theorem, if you look at, say, Anderson and Moore, the main reference I mentioned last time. So under stabilizability, detectability, and if M0 is a positive definite, so you don't actually need to be a Lyapunov function, just a positive definite function. Then what's going to happen? Well, we see the 8 ends decrease. So these 8 ends defined in this way, they're decreasing and they converge to a star. But note that this is true for any sigma. And I can fool around here and I can choose different noise variables. But if what I choose for the covariance, I'm going to get this decreasing property. And in fact, what you find out is that Mn itself is actually decreasing. So the matrices M themselves, these Lyapunov functions themselves are decreasing to the to M star. Okay. So these converge. They converge in a decreasing way. Okay. And what I mean by this, I think I've used it before, but just to remind you, when I say that Mn is greater equal to Mn plus 1, I just mean that just means that the difference is a matrix which is positive semi-definite. And so you've got these decreasing matrices that converge. So what you get is a little bit stronger. And but the big thing is, again, the whole algorithm, variability plays no role at all. Do you see any variance in this here? These MNs converge to M star, and variability is absolutely irrelevant in the equation. It's important in the average cost, of course, but the value function is independent of the variable. And just it's a sort of a theme that often variability is not that important for control. Sometimes it is, sometimes it isn't. And for linear systems, in this fully observed case, we can observe the state, the variability is, you can ignore it, pretend it's not there when you design the control law. All right. That's it for part one of the course. Part two of the course. Questions?
It's actually mn plus 1 equals a on the bottom line, the second line.
No, you're thinking of value iteration. So the value iteration we had mn plus 1 was that.
I mean whether it should be mn plus 1 equals a transpose.
No, that's value iteration. So for value iteration we had n plus 1. But if we want to solve Poisson's, this is a solution to Poisson's equation. And this is a Lyapunov equation. So for a linear system with quadratic cost, the Lyapunov equation here is equivalent to Poisson's equation. So it's very different. So here you're solving a system of linear equations. Well, with value iteration, you defined mn plus 1 this way. And so you can see actually you can see right away it's simpler. This is having to solve this linear equation in each step is more complex than value iteration. Right? Let me write that down. This is PIA. They are different. Here you solve a linear equation, and here you just update. And so the complexity is much less. And so that's excessive approximation, and that's Newton-Raphson. Now, I've never seen this written down anywhere. Let me have a go. I don't think I've ever voiced this in public. Policy iteration is Newton-Raphson, and value iteration is stochastic approximation. And we know that for value iteration, I know that Mn goes to M star geometrically fast under these conditions, under stabilizability, detectability, and a positive definite initial condition. And in fact, one way to say that is that the limit as n goes to infinity of 1 over n times the logarithm of mn minus m star is strictly less than 0. Now, I know m is a matrix, but just vectorize it as a big vector. So we start with the norm. There's a difference between two vectors, okay? So when I say something goes to 0 geometrically fast, it means if I take the log, it goes to negative infinity linearly. And that's why you often call this, you often see this called linear convergence. Now, conjecture. I don't know why I've never done the work to actually prove this. I'm sure it's true.
Why would you have taken log?
Yeah, because because if let me write this. If I take rho to the n, that goes to geometrically fast, the thing goes to infinity. Well, what's 1 over n times the log of rho to the n? I like that. Yeah, that's the idea. Yeah. So that's one. When I say geometrically convergent, I mean the case like like rho to the n for somewhere less than 1. The equivalent way of saying it is this: if you take the log and scale by n. Now it's known. I'm writing conjecture here for PIA. And I'll put a limb soup there. The limit might not exist. Maybe it oscillates around. For PIA, what would we expect? Well, if you look at the Anderson and Moore, it'll say it goes to 0 geometrically fast. So the same thing holds. But that's not what you'd get if you pick up any book on convex optimization. You would get 1 over n squared. But that's the conjecture. I'm sure that must be true. Because Newton-Raphson has that property. Newton-Raphson, the reason that people in optimization are so excited about it is that it doesn't have linear convergence, it has quadratic convergence. That's what it's called. If you pick up a book on convex optimization, those are the definitions you'll see. Now, and the conjecture is right there. Newton-Raphson is known to have this much, much faster convergence. It's like saying the error, instead of being like rho to the n, it's like rho to the n squared. And you see that, you say, Jesus, that's fast. In practice, I don't know if it's meaningful. I made a joke about this once that we have limits on floating point accuracy and so forth. It's hard to know what it means. There are constants involved. There's a constant times that, maybe a constant z, which I don't. But I'll bet you anything you get this quadratic convergence for Paul's equation. So, and you do see amazing fast convergence. I mean, you see. When you run Paul's iteration, you'll find often in 5 iterations you've solved it. Well, in all the examples I've looked at with value iteration, you can go 1,000 steps and you're not finished. So there is something amazing. I don't know if the theory here explains it. But the computation each step can be significant in algebra. I've never seen a comparison of a linear case. So I don't know what the best way to do it is in a linear case. It's not a minor. Okay? So it's a conjecture, and if any of you have lots of free time, I'd love it. Anyway, I can give you references. All right. So, So you've learned everything that I want you to learn about Markov chains and Markov decision processes. And now there's a big lie in the room, So up to now, we have a big black box. We have an input U. There's some noise. We have X, and we close the loop. There it is. So this is the point of view we've taken. We have this system that we can model with input U and ID noise, and we observe the state and we apply the feedback. And the big thing here is, most of the time that's absurd. And a lot of things are absurd, I don't mind. It's absurd that the n is ID. I mean, give me an example. It's never true. But like we just saw in the linear case, there's incredible robustness to disturbances. So it doesn't bother me at all. It's to pretend it's ID to get some, to get in the ballpark of a good policy. In the end, I'll do some simulations based on real data and maybe try to refine my solution. So NID. Now, I've said that before. And the fact that even probability is even a myth. Just like F is not equal to MA, nothing's Gaussian. There's no such thing as probability. These are modeling tools. These are modeling tools. They give you incredible insight, but there's no God flipping a coin. That's what I'm saying. There's no perfect coin flip. But the biggest thing is X. I mean, Jesus, to think you can observe the whole state is just crazy. I mean, of course, in many cases you can pretend, and it works. So, the big issue, I'm starting off with estimation. Basically, we don't know the state and we'd like to estimate it. The learning is something else. It's basically how we would approximate value functions, things like that. How do we approximate solutions for dynamic programming equations in really complex settings? And we've got all sorts of tools for doing that. But first, we've got to talk about state estimation. So, X is frequently not observed. I mean, the simplest case. Now this sounds like a joke. I've got a sensitive position, not for velocity. Of course you'd say, well, God, differentiate your position gets your velocity. But there's no X. You differentiate the position, you get jump. And you can do much, much better by using structured model to take that into account. But that's example one. But example two, I mean, most of the systems we care about are really big. I mean, do you think that the power grid is centrally controlled? So I would guess that my state process is an R to the 10 to the 10th power or something. It's just there's no way you could even think about a state so small. So the approach is, by far the most common approach is pretend. Okay. That's what's done in the power grid. Six. You take a power plant and you look at some regulation signal, say, and you want to ramp up and down, say, a coal generating coal plant, and you pretend that your observed variables near you are the real system, and you design a LQR controller based on that pretension, I mean that supposition, not pretension, that supposition, and it works sometimes. It often works. And may not. So in the case of the power grid, nobody's ever attempted to justify these assumptions. In every county of the country, you've got control systems based on this assumption that instead of taking the huge complex power grid network as a system for that, you just take your observable variables, pretend that's the real world, and design a controller. Again, I don't know how you could justify it. I have feelings that if you're conservative, then you can probably have a theory to predict where it goes. Like if if you're very low gain. You put a very high cost on control, so your resulting feedback laws are low gain. Then I bet there's a theory to justify this approach, but I've never seen it. There's no paper out there that I know. So, but that's what's done in most cases. So, I'd be ashamed to have spent so much time on this if I had to say, throw away everything you've ever done. Because in most cases, you just pretend. You just take a bunch of observables, pretend that's a state, and if it doesn't work, add some more observables. Just increase the state some more. But two is refine the model. So I'll keep with my original x of t plus 1 equals some function of the past state and the input and the noise. We're assuming we got this from physics or through some experiment of some sort. But now I've got an observation y of t, which is going to be some function, say g, of the state and noise. So I've got system noise and I've got observation noise as well. And so when I say pretend 10 to the 10th equals 6, so these are observations. So in the case of the power grid, these are the voltages nearby, maybe some regulation signal from the center of the power grid. This might be 6-dimensional, and you pretend something like this is the state. Now there are no state dynamics; you'd have to fabricate them somehow, but you just get an approximate model. We'll talk about that. We'll talk a little bit about that somewhere. But here we refine the model. We just explicitly say, I'm not allowed to take u equals c of x. U has to be a function of the observations. It's both beautiful and hideous. It's like Ellis Lake. You can see egrets and cormorants and these alligators going by, and sometimes it smells so bad you just want to run.
Is this something like HMM?
What's that? Well, HMM's part of it. So let me get to that. Yes. So what's the terminology? Let me go down a little bit more to be precise what I'm talking about. So I have a restriction now. I'm still recovering from the jog. And there's some notation here. That I'm borrowing from stochastic process literature. And if you haven't had a stochastic process, of course, don't worry about it. When I say u of t is in y sub t, I mean u of t is a function of the past observations. And then what we call this is a POMDP. And so the question was, is this a hidden Markov model? Well, an HMM is, yes, it's this, but without control. So HMM is the process Y when there's no control. So just like we had Markov chains, and then we had MDPs, we have HMMs, and we have POMDPs. So, we could spend an entire course on the theory of HMMs without any control. This is a class of stochastic with no control there. This is a class of stochastic processes that just receives a lot of attention. But we're gonna go straight to the control things.
The difference with Markov chain, HMM.
Well, okay, yeah. Let me say a few things about that. Now, if you look at these two things together, exercise, so if you look at x of t and y of t together, it's a controlled Markov chain. Just put these two equations together. Xt plus 1 is a function of the past state variable, control, it's a noise. Y of t plus 1 is a function of x of t plus 1, but x of t plus 1 is a function of past. And so I'll put that as an exercise. So if there's no control, so if u of t if we freeze, when I say no control, let's just take this model, freeze this, period. Then of course this will be a Markov chain. So your question's legitimate. What's the difference? The pair process of Markov chain. Now the idea is this: is that why are HMMs important? Well, the idea is this: I might have a process, a y of t process that takes on like two values. Now, what I'd like to do is and I take observations of this, I'd like a nice model of the stochastic process, y of t. If I take y of t itself to be Markov, I don't have many choices. It's way too restricted. So I'd like to come up with a class of algorithm models that's a little more complex that can capture some dependency. So an HMM, y of t, y is Markov is too restrictive. I've got a lot of degrees of freedom in modeling. So even though y this takes on two values, I can model a lot of dependency. The fact that if y is 0, it's going to stay 0 for a long time, then hit 1 to be 0 again for a long time, then be 1 for an hour, then be 0 for a long time, then be 1 for just a second. I can model some really weird, funky dynamics. Well, if it was if y were Markov, it would stay at 0 for a geometric amount of time, jump, stay at 1 for a geometric amount of time, jump. Well, what if I wanted it to model be uniformly distributed at 0, and then uniformly distributed? Well, that I can approximate by the Markov model. And so it's a very flexible approach to modeling. You can model some very complex dynamics with a fairly simple hidden Markov model. That's what's claimed. That's the idea and there are also really nice algorithms for fitting. So I can take observations of y of t, and there are algorithms to compute a good f and g. So, you know, so they get a good approximation. Yeah. So, all right. Any other questions? Yeah. All right. So it's just a flexible approach to modeling. And I think maybe that's, you know, the best motivation for you is that you might be able to, instead of going with a really complex state, you know, if you're lucky, you can get away with a 5-state X and a 2-state Y and solve the problem, you know, and you'll have to just use some fancy algorithm to you might not use physics, you'll use, you know, compute G and F through, you know, look at Wikipedia, through Baum-Walsh and other algorithms for estimating F and G based on measurements. All right. So what's pretty and what's ugly? I'll tell you the ugly first. The Markov theory to come is ugly. I'll explain why. Maybe I won't. There's one thing that's ugly, is that when you actually, the natural approach to deal with these partial observed Markov processes leads to some structure which is completely not understood. It's just still, you know, completely, there's just a frontier out there. But what's beautiful, and I don't have as much time as I'd like, but for any of the control, we're going to be able to look at all the control problems that we've looked at before. So we can consider discounted cost, average cost, fine horizon cost, all the control criteria was before. So just everything can be defined in the same way. I'm trying to minimize the expected average cost, or minimize the cost up until some defined time horizon. Oh, any of those things at all. Well, where is it? I do know that the optimal control is equal to this horrible function. I should have used a different color for ugly. Now that's ugly, right? That's ugly as hell. But it turns out this is also equal to some feedback law of some I of t, which is called the information state. And it's fully observed. So it turns out we can take this problem that's so ugly and we can transform it into a fully observed Markov chain, controlled Markov chain. And what I mean by the Markov theory to skip is that, yes, it's a Markov chain, but none of the theory we've developed in this course applies to it. There is no theory for it. It's a weird Markov chain. So it's, I ran out of time, unfortunately, because of the pen accident, but we'll get to this. Some of you already know what I'm going to say, but and moreover, I can write down I can write down the expectation of C of X. Let's forget U for a second. I can write down that expectation as some function forget my T here. So you give me any cost function X for the original system, I can translate that to a cost function on the belief state, and see how it's linear. You know? And so how would I get an optimal? I'm not going to tell you what this is yet. This is no time for it. But I claim I can create this crazy information state, and instead of having to look at this increasing amount of data, I have just one IoT. Because I can basically construct a fully observed control Markov chain, and that's it. And the cost, which originally was quadratic, now is a linear function as a belief state. You know? And I have, obviously, to get phi star for average cost, and that's supposed to be ugly, and that's not ugly. Obviously, phi star of X is going to be equal to the arg min over U of what? C of Xi. Right? If I'm claiming now I've converted this problem to a problem with a fully observed Markov decision process, the cost on X can be translated to cost on I. So it's fully observed. I've got a theory now. Just pick up everything we've done before. We know that the optimal policy is obtained for this. It turns out 8 star has some beautiful properties. C was linear. 8 star is concave. That's nice. You know, I told you I like convexity in my value functions because it's sort of the natural ways of approximating. I can approximate by quadratic or, you know, something, things like that, an exponential, things like that. So the fact that this, when you do this, you get a nice structure for the value functions, really pretty. You know? But there's always a cost, and it's the reason this is ugly is that I is in a huge state space. You know. I don't want to say it now. Half of you know what I'm going to say. I'm just going to leave the mystery for the rest of you. I wasn't planning to say much more than that. I just wanted to give you some details. But I'll come with my pens next time, and and I'll explain that. So yes, I is a conditional distribution. It's a belief state. for half of you to know this. And I'm not going to do very much because, like I said, it's a frontier. You know, there's so little known about how to solve these things. So I want you to know what it is. Of course, in the linear case, it's all easy. In the linear case, the whole thing is a beautiful solution. But in the general nonlinear case, I'll wait for somebody to have a breakthrough. I'll have a whole career simple. Until Friday.